Hey Hawks, this is Mr. Moog from Hanover. I'm going to take you through our notes on 5.4's Learn from Home Materials. It's the application of quadratics. It's just a one-page practice sheet, and I'm going to give a little explainer on this stuff. I'm going to go through how to do this stuff using Desmos, because this is the easiest method. I'll do both problems only using Desmos, and then I will go back through both problems using Algebra. So we're going to solve them the algebraic way. So I'll do both ways. The Desmos one will be first. So if you're only interested in that, you can watch through that and then be on with your life. So to get into it, the application of quadratics, first of all, we should understand that we are working with quadratic equations. So we're looking at parabolas that go up or down. In the real world, oftentimes because of gravity, the path of something flying through the air will look like a parabola that's going downward, or it's what we call concave down, honestly. So this one doesn't necessarily apply all too often in application that we're going to talk about, but here that's what you should expect to see on a graph. Other big things to know on that graph is we have a vertex, what we really can also call the vertex is a maximum or a minimum, also shown by this highest or lowest point on the graph. And then we also have an x-intercept. So x-intercepts, those are the zeros, those are the roots and solutions. So we've been finding those for a long time. Just look where the graph touches the x-axis. So zeros give where the projectile hits the ground. So applying that into the real world, what it's talking about is a vertex is the height that is the highest throughout the whole flight. So the vertex height would be the y value that's talking about the highest point through the air. And then the x-intercept gives where the projectile hits the ground. So on this side over here, let's pretend that we had a graph running through here. This dot right here is an x-intercept, and you can see the x-axis is essentially the ground there. So we want to figure out when would something hit the ground, or water, or something else like that. So two important things to know about talking about this graph here. So you may use Desmos to find the characteristics or use algebraic methods. Once again, I'm going to talk about Desmos first, and then I'll get into the algebra methods afterwards. So I'll come back to the algebra stuff after I finish the Desmos stuff. So for number 11, we have a tennis ball is hit upward with a velocity of 48 feet per second. The height of the ball after t seconds is given by the equation h of t equals negative or positive 48t minus 16t squared. Sorry, I got the negative in the wrong spot there. So 48t minus 16t squared is our equation. So if we're in Desmos, the first thing we're going to do is just type that equation in. So I've got my Desmos on my screen here. I've typed in both equations for 1 and 2, so I don't have to spend time typing that in. So if I just click on the little circle over here and show you that graph, that doesn't show me much. It doesn't look like a U, it just looks like two straight up and down lines. I can see some gray dots. But what I first want to do is make this graph fit on my screen. That's not very helpful. So one special thing you can do on Desmos is you can grab the y-axis. Let me just get rid of that. The y-axis only, and if you put one finger on the y-axis and take the other one and move it up or down, it'll just move the y-axis, not the x-axis. So now, when I bring that graph back, you can see something actually useful. It's got 3 gray dots and it's in the right shape there. So there's our graph that we're going to be looking at. Let me slide that over. It says, how long does it take for the ball to fall to the ground? So once again, the ground is occurring at an x-intercept. So all we really have to ask ourselves is, do we want the x-intercept on the left or the x-intercept on the right? Well, the first one's 0, 0, and if we apply this to a real-world problem, that's saying that the ground, or that the ball is on the ground when it's 0 seconds into its flight, And then over here, the ball is on the ground when it's 3 seconds into the flight. Well, we knew the ball was on the ground at the beginning, so we don't really care about that point on the left. So I'm just going to scroll away from it and only look at the point on the right. And you can see, once again, that that's 3 seconds. So the ball hits the ground 3 seconds later. That's how you could write that answer in words and interpreting it, and that's 100% done. The second part of the question says, what is the maximum height of the ball and when does it occur? So this is a two-parter. It's asking you for height, that's a y value, and when is an x value. The other thing that's important here is this maximum should tell us, look for the vertex. So, looking back at my graph, my vertex always occurs at the highest point. So I have 3 gray dots, and the nice thing about Desmos is it gives it to us. So my vertex is 1.5, 36. And so 1.5, 36 is the ordered pair, but we want to write that into the application of this. So I'm going to go ahead and move my phone out of the way for now. What that tells us is 1.5 seconds into the flight, the ball is at a max height of 36 feet. So there I've interpreted everything. I've talked about when, I've talked about what the ball is doing, it's flying through the air, and how high it went at its highest, so the maximum height, 36 feet. I've got units, I've got all the right numbers, we're done. Sliding down to number 12. Number 12 says the max height of a baseball in feet t seconds after it is hit can be modeled by the function h of t equals negative 16t squared plus 96t plus 3. So, once again, I'm going to look at Desmos. I'll get rid of that red graph and pull up my blue graph, the one that applies to this question. And once again, when you just type it into the normal Desmos, it doesn't show you much that's helpful. So once again, I'm going to hold on the y-axis and slide it down. This time I need it to actually be pretty big. So I'm going to go from 0 to 200. And if I click on it, now I can actually see the path of that ball flying through the air and how high and all that it gets. So to find the maximum height of the baseball, we're looking once again for the vertex, but this time we only care about the y. They didn't ask us when, they just had said what's the height. So if I go back to Desmos, click on my vertex, that highest point, all I really care about is my y. And actually, if you see my numbers are a little off, it's because I typed it in wrong. So it should say 96 right there. So if I click on that, my y value is 147. So what that tells me is my maximum height is 147 feet. And that's part A. Part B says, how long does the ball take to hit the ground? So ground, once again, is where we're looking for x-intercepts. And I don't care about this point on the left. It's almost always in these applications, the point on the right. So I'm going to click on my x-intercept. I'll get rid of that vertex there. And all I care about is the x value, so 6.031 seconds later, the ball hits the ground. So really, when it comes to applications of quadratics, it's just being able to interpret a graph. So if you know what the vertex is, it's talking about maximum height, and you know what x-intercepts are, those are talking about when it's hitting the ground, then all you got to do is look on the graph for Desmos. So if you are good with just checking it out through Desmos, you are good to move on. If you want to hear the algebraic explanation, so going through the math of it, I'm happy to do that as well, and I will continue that now. So looking back at number 11, we've already answered the question, so really we're just going to check our answers using algebra. So A says, how long does it take for the ball to fall to the ground? Well, if we come back up to this box, it tells us the two algebra things that we need to do. So determine the vertex. I'm going to use this equation, negative b over 2a. So that looks like a piece of the quadratic formula because it is. It's that first part on top and then the whole denominator 2a. So we're really just using a piece of the quadratic formula, and then once we get that, we'll find the y value by plugging in an x. But that first question didn't ask about the vertex, it asked about our x-intercept. So in order to find the x-intercept, we're just going to use our favorite methods, factoring or the quadratic formula. So I'll write that here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So, x-intercept, factoring, or quadratic formula, well, my equation here is 48t minus 16t squared. And the one important thing that we need to know algebraically is where the ground is in terms of h. So ground in terms of h means h equals 0. So instead of saying h of t, what we really need to do is change that into 0. Now we're actually looking at the ground. The height of the ball is 0 feet off of the ground, which means it's actually on the ground. I'm going to factor this equation because we have a t here and two t's here, so they definitely have a t in common. And then 48 and 16 actually do have a number GCF as well, 16. So 16t is my GCF, 48 divided by 16 is 3, t divided by t is no t's. Negative 16 divided by 16 is minus 1, but I'm not going to write the 1 because there is still a t left. So t squared divided by t is just t. From there, both factors get set equal to 0 by themselves. And now you can solve both of them to find t equals 0 and t equals 3. Well, if you remember, looking at the graph, there was two answers. We're always looking for the bigger t value when we want to know when the ball hits the ground later. So because 0 is the smaller number, 3 is the bigger number, the answer here is 3 seconds. And that would be the algebra for solving 11a. Sliding down to part B, we once again need to figure out what we're doing, and then we can figure out how to do it algebraically. So it says, what is the maximum height? We have already indicated that is what we're the vertex. We're looking for the vertex here. And they want both the height and when it happens. So we need an x and a y, and we need to find those by looking at the vertex. So algebraically, the vertex, I'll do this one in pink, comes from x equals negative b over 2a. So first thing I need to do is I need to go to my equation and find b and a. Well, this h of t is kind of in the wrong order. We always like to put it in standard form with the highest degree first. So I'm going to put negative 16t squared plus 48t. And I'm also going to put 0 at the end, plus 0 at the end, so that I have my c there. Now I can find a is negative 16, b is 48, and c is 0. If I were to use the quadratic formula, those would be all the pieces I would need. And now I can plug in and find the vertex x. So x equals negative 48 divided by 2 times negative 16. And if you have a calculator or you like solving fractions, really that is 3/2 or 1.5. That checks out. We said 1.5 seconds. The x we got by doing it algebraically is 1.5 seconds. Awesome. But that's not the end of our problem. So unfortunately, I'm going to bump down just below into part 11, but that's okay. We now need to do h of 1.5. All that means is in this equation h of t, we're going to plug in 1.5 to all the t values. So negative 16 times 1.5 squared plus 48 times 1.5, and I don't need to write plus 0 this time. If you type that into your calculator, you will get the height 1.5 seconds into the flight is in fact 36 feet. So algebraically, it checks out that we are at 36 feet, the maximum height, 1.5 seconds into the flight. All right, and 12, pretty much the same process. It's just going to look a little bit different because we don't need all the pieces that we did last time. So 12 is asking us to look at a different flight using the equation h of t equals negative 16t squared plus 96t plus 3. The nice thing about this equation is it is already in standard form. So that's good. So if we're looking for A, B, C for the quadratic formula or the vertex formula, we're good to go. So part A is asking us to find the maximum height, which we've already indicated is going to require us to find the vertex. So we're going to use that formula x equals negative b over 2a. But look at what the question's asking for. It's asking for the height. This formula only gives us time or when. So we're going to have to use time to get the height. That's the unfortunate part about the algebraic method, is sometimes you have to do more work just to get the actual answer that you're being asked for. So we're going to need to find time, and then we can find the height after that. So from our standard form equation, I'm not going to rewrite it. I'm just going to find A, B, and C. A is negative 16, B is 96, and C is 3. In this equation, I don't need C. I'm just plugging in B and A. So we have x equals negative 96 divided by 2 times negative 16. And that right there is 3. You can type it in your calculator. You can solve it however you want. But that answer ultimately does come down to 3. But that's not our final answer. That is a time, 3 seconds. Ultimately, what we need is the max height. What max height really is when we take our equation and plug 3 into it. So what we're going to need to do is find h of 3 by doing negative 16 times 3 squared plus 96 times 3 plus 3. This will be our actual answer. And that does come out to 146. It's in feet. When you crunch that number, you do get 146. I just put feet on it because we are looking for an actual number in the real world. That checks out from our Desmos answer. And so the method there for finding the vertex x value and then plugging that in works just the same as we did before. We just only need the height portion to actually answer this question. The last part of this, the last algebraic part of this, is unfortunately the longest because it's got to use the quadratic formula. So it says, how long does the ball take to hit the ground? So we're looking for the x value, x-intercept. So basically all we need to do is plug into our quadratic formula. It starts with x equals, then it's negative b plus or minus the square root of b squared minus 4ac all over 2a, which we've already found a, b, and c. So we're just going to go down and plug all that stuff in. Negative 96 plus or minus the square root of 96 squared minus 4 times negative 16 times 3 all over 2 times negative 16. That is something we can simplify. I will first start under the radical, and we get negative 96 plus or minus the square root of 9,408. It's a positive number, so I know I have two real answers. All over 32. I got rid of, didn't get rid of it. I just forgot it. We have a negative 96 and a negative 32, so ultimately those negatives will cancel each other out. But first we need to simplify 9,408 under a square root, and that would require us to do a factor tree. If you want to practice factor trees, you can go through the notes that we've done. We did that back in class. I'm going to shortcut that and just go down to the final simplified version of this radical, which is 12 plus or minus 7 square root of 3 over 4. This is actually not our final answer because it actually is two answers. So if you remember that plus or minus makes two answers, we get negative 0.31 and 6.03 from this. Well, I know you know the answer already, but let's think about this. Do we care about a negative time? We do not. So our answer is only the positive number time. And we also always want the bigger time value. So our t algebraically is 6.03 seconds. It will hit the ground, the ball will hit the ground after just over 6 seconds of flying through the air. So the quadratic formula is what we could use there. The reason, once again, is because we want to know when the ball hits the ground. When it hits the ground is either done by factoring or the quadratic formula. And this formula here actually cannot be factored. We can't do two-step or grouping or GCF or any method like that. So instead we had to use the quadratic formula. So that is quadratics applications. I hope you were able to follow along and do well on your final assessment for this unit.